This is the post-lab discussion for the ramp lab that we did in class. We did have this discussion in class, but for those of you who are either absent or if it was a little fast for you, this was kind of an in-depth lab discussion. Here's a recap for you. Hopefully maybe the second time it'll make a little bit more sense. So when we did the lab, you should have come out with an equation for the velocity time graph and an equation for the position time squared graph. Both of those should have been linear, and therefore you should be able to make an equation for them. So this is an example equation. You have your own equation. This is just one with made-up numbers so that we can look at it. Things to pay attention to is you should have the correct variables, which here is velocity and time. Remember, you can never write an equation using x and y. X and y are general variables. We're looking for variables for the relationship we studied, which would be velocity and time. So never, ever, ever write an equation in physics class using x and y. Okay, so you have the correct variables, v and t, and then you want to look at the units for slope, which should be centimeters per second squared. Unless you used meters, you could have meters per second squared. Either one of those would be fine. And then the y-intercept would have the same unit as what's on the y-axis, which in this case is centimeters per second. In my example, I went ahead and eliminated the y-intercept by the 10% rule. That may or may not be the case depending on your lab. So now that we have a sample equation to look at and we've made sure the units and variables are correct, we can take a little bit and try to figure out the general equation. The difference between the mathematical equation is that the mathematical equation has numbers and units. The general equation, so mathematical versus general, the general equation will have only variables. So the goal is to look at everything that's a number, figure out what it means, and then replace that variable or that number with a variable, so that you can use the equation to predict physical behavior not just for your lab sample with a specific numerical slope and y-intercept, but an equation that you can use in any situation involving the variables from the lab. Okay? So for our general equation, we can first talk about what the slope means. That's the first number that we need to interpret. Slope here means acceleration. You know this because of the units are centimeters per second squared. If you didn't already know that was a unit for acceleration, that's okay, but you should know that pretty much from now on because we'll use acceleration a lot in this class. So anytime you have a distance divided by a time squared, regardless of what the units are there, that would be acceleration. So acceleration is our first new term for the chapter, and the definition of acceleration then is the rate of change of velocity. Things you should know about acceleration. It's a vector quantity, so the direction does matter, the sign does matter, and acceleration in physics refers to not just speeding up, but speeding up and slowing down. So we'll have to be careful to note that when the acceleration is talking about a change of velocity, but that change could actually be something slowing down. And lastly, as a note here, we will only study constant acceleration in this class. So based on the units, we said that the slope must mean acceleration. So then the next question is, what does the y-intercept mean? The y-intercept must be the initial velocity. Here on this pretend graph that I have, it looks like it's about 0, but wherever the y-intercept is would be the starting velocity for the situation that you're dealing with. So that'll always be true. The y-intercept is always the starting something. So in this case, since it's velocity on the y-intercept, it must be a starting velocity. So the equation for any line is y equals mx plus b. In this lab, we studied velocity and time, so I've subbed those in for y and x in this case. Now that we know the physical meaning of the slope and the y-intercept, we can continue and sub in for m and b. So note, this is not the general equation, this is an intermediate step. So we'll move ahead and look at the general equation from here. So here you have that. Notice this 0 here should be a subscript v, like a v sub O. I just can't get this program to recognize that when I import it. So what you have here is v, the first v being the final velocity. Some different textbooks or curriculums may use VF for that. The one that we use is just going to use v. The VO is then the initial velocity, and again, another curriculum might use VI. So we're going to see that as VO for initial velocity, V for final velocity. By the way, in the last chapter, we studied the equation x equals Vt plus xo. We didn't make a big deal about it at the time because it didn't matter, but technically the v here is actually average velocity, which is usually represented with a line above it. So, and that's why this equation is only good for constant velocity, because the velocity in the equation is an average velocity as opposed to the velocities here, which are two specific times, the initial and the final. So that's something to be watchful of. So oftentimes you'll see the same equation written solve for acceleration. We'll see it both ways in this class. You shouldn't have any trouble between the two. So acceleration then is the change in velocity over time. If you haven't seen this notation before, the little delta sign, the triangle just means change in. This is not easy to write on. So change in velocity in this case. And the change in velocity then would be the final velocity minus the initial velocity. And as far as which equation is your general equation, I like the one in red because it follows the way that your graph is set up. But this is actually the same thing as this. So this one would not be wrong, but I like the one in red just because it's the form of the line that you wrote. So here's where it gets a little more tricky, is we're going to look at a few things on the velocity time graph and see if we can relate it then to our position time squared graph. So follow what I'm doing here. You won't have to repeat it on your own, but it's something that you should at least be able to follow and understand. So if you don't understand it, you should definitely ask, but you won't have to actually repeat it all by yourself. So the first thing to know is we're trying to write an equation for displacement. So we're writing an x equal equation. So we know if we start with a velocity time graph, the x equals the area underneath the graph. So I'm going to break this area up into two pieces, into a triangle and a rectangle. So I did mine in blue and green, and so we're going to go ahead and see if we can find the area of both of these. So for my rectangle in green, I can say length times width, and for my triangle, 1/2 base times height. So that should be okay. And then I'm going to sub in the variables that I have for this particular graph. So my length on my x-axis is time. So that's why I put that in there. My width is going to be VO. It'd be VO minus 0, which is just VO. And then plus, my triangle is going to be 1/2 base times height, where base again is along the bottom. And the delta V I got from saying V minus VO, which equals delta V. So this distance from there to there is actually delta V. So I've got that all subbed in. Now I'm going to do one little substitution because I know where I'm trying to go with this. I'm trying to get an equation that has acceleration and displacement in it. So I'm going to do one little substitution. So we said before that acceleration is a change in velocity over time. So if I go ahead and rearrange that for delta V, I have a delta V up here, and I can substitute that in. So I'm going to say delta V equals acceleration times time, and then I'm going to go ahead and sub that in here for delta V, and that helps me get acceleration into this equation. And that's one of those things you wouldn't know to do unless you knew where we were going. So again, this is something that you should be able to at least follow. So I've done that on this next little black equation here, this one, and so I have AT in where I had delta V. So now I have a quantity here with two t's in it, and I went ahead and combined those into t squared. So this is how that equation would look put all together, and that is the general equation for the xt squared graph. I should put a little 2 there. So that's where all that comes from. And again, whenever you see these little zeros, those should be subs. I wish I could make the computer do that right. So that's our general equation, and so we're going to look then at our xt squared graph and try to make sense of that from the equation that we got. So now we're going to take a second and work backwards. We got the general equation from our derivation, and we're going to compare that to what I have as a sample equation here. So if we we're going to look at both the slope and the y-intercept. For the slope, you can see that the units are centimeters per second squared, so that's a unit for acceleration. So it would make sense that the slope means acceleration. The thing that you can't see in there is that there's a 1/2 in there. And that's the reason that we worked backwards from the VT graph backwards to this relationship to look at this one, so that you know that the 1/2 has to be there, because when we found the area of the triangle, there's 1/2 base times height, so that's where you get the 1/2 from. Since 1/2 doesn't have a unit, then it just doesn't show up in the number for us to see, but that's how you would know that it's there. The y-intercept then, it is centimeters, so you think it's just a distance. Specifically, it comes from something in the lab, and that is velocity times time. If we take a look at the initial velocity, that's in the unit centimeters per second. If you multiply that times the unit for time, seconds, the seconds would cancel out and you would get centimeters. So that's actually where the centimeters comes from in this y-intercept. So the physical meaning of the y-intercept is actually initial velocity times time. So the question we need to answer for the lab, the whole purpose of the lab, was to find the relationship between displacement and time and velocity and time. So from our linearized graphs, you should see that that displacement is proportional to the square of time, and velocity is directly proportional to time. You know both of these because you have linear graphs. So if the experiment were performed again, what could you do to change the slope? I'll let you think about that, but we know that the slope is the acceleration, so I'm not going to answer that here. What could you do in the lab that we did to change the acceleration of the car going down the ramp? Make sure that you include what you would do and what effect that would have on the acceleration. So you should be able to say, if I do this, it will increase the acceleration or decrease the acceleration. So be specific in your lab report. How could you change the y-intercept? We just talked about what the y-intercept was for the velocity time graph. So, and you don't have to answer this for both graphs. For these, just answer it for the velocity time graph. But how could you go ahead and change it? Lastly, you need to think about any types of error that could happen in the lab. Doesn't mean you did a bad job, but to recognize the limitation of the equipment that we have, what are a few errors? And that's something you should be able to figure out on your own.